Hello, and thank you for joining me for Chapter 4 in our lecture series. This is going to be on igneous rocks and plutons. So in this lecture, we're going to cover magma and how it's composed of silicon and oxygen. There are a few exceptions to this. We're going to talk about the temperature and composition, the most important controls on the mobility of magma and lava, which means it's going to be either thick or thin, and that's going to depend on high temperature or low temperature. We're going to look at how magma originates in the Earth's upper mantle and lower crust and how this usually occurs near divergent or convergent plate boundaries. We're going to talk about chemical changes in magma and how magma evolves. We're going to talk about how lava cools and crystallizes, giving us different types of rock. We're going to talk about how geologists use texture and composition to classify igneous rocks, and then we're going to talk about how intrusive igneous bodies called plutons form deep down in the earth, and it usually cools slowly, so they have fairly large crystals when we normally think of these as granite or something like that. Now here we have a picture of a big granite mountain. It's probably in California. I don't know where it is, but it's the figure from the book. And most of the continent is composed of igneous rocks. Most of these igneous rocks, at least the ones that are on the continental crust, or which make up the continental crust, are composed primarily of quartz and feldspar, um, with varying degrees of different minerals. So you got darker minerals like olivine and pyroxenes, which are also found in granite, but just to a lesser extent. Primarily, granite is composed of quartz and feldspar. And we have the properties of magma. So when we know that rocks melt and they turn into magma, depending on where they emerge or where they're cooling, they'll have different colors, or actually the shades, I should say. It's not colors, but they tend to be darker when they contain more iron and magnesium. That's why we call them ferromagnesium rocks. And in this case, if you're looking, well, let me get my pen. Here we have in rocks that, so think of Hawaii, or the rocks that you would find in Hawaii. They're composed primarily of silicates, but a large constituent of those minerals, we talk about the chemical composition, is calcium, iron, and magnesium. And those are usually found in ultramafic rocks, which is, in this case, what they have is greater than, or sorry, less than silica, less than a 45% silica content. And as the silica content increases in this direction, you move from sort of that oceanic crust, sorry, it's getting kind of funky there, to the continental crust. I'm just going to say continental crust like that. And as that happens, the rocks get lighter, and once you get into the felsic range, they tend to have a greater than 65% silica content. So if you look at the properties and behavior of magma and lava, you'll notice that it's going to be related to viscosity. Viscosity is how thick it is. And so in this case, if you can see over here, in this area, the magma is sort of spewing out and spraying, which means it has a very low viscosity, and it's running like water as it comes down this direction, which suggests that the lava actually has a very low viscosity, which means it's probably going to be hotter. Just like any time you heat up anything, it's going to run faster, and it's probably going to be composed more of the magnesium and the irons that we're talking about, and this is evident by, if you look at all this rock down here, it's pretty dark colored. The mafic magmas have a higher concentration of magnesium and iron and things like that, and the minerals that form there under these conditions tend to be more robust to melting. Here we have felsic lava. If you look, the felsic lava is very thick. So this dome right here that you see, this is lava. And it's similar in consistency to the lava that came out of Mount St. Helens when it erupted. And due to the fact that it has a high viscosity, which means it's very thick, it almost looks like rocks, but this is still going to be sort of runny. Well, it's going to be like taffy, actually, or much thicker than taffy. This has a very explosive reaction if it were to go, and there would be a big bubble of gas underneath because it's going to build up pressure and not release very rapidly, where if you look at the lava in Hawaii, it tends to be runny and and gets released very, very quickly, or the gas does. Which leads us to Bowen's reaction series. Now, Bowen's reaction series is basically a series of how minerals form at higher or lower temperatures, and then what chemistry is used up. And well, basically what Bowen did is took a bunch of different kinds of rocks, melted them, and then cooled them and evaluated at what point certain minerals were formed. So here you have olivine, which forms at very high temperatures and probably high pressures, because that's the constituents that we're talking about here is high pressure, high temperature at this level. And then, of course, over here you have this continuous side, which is calcium-rich plagioclase, which then goes down to the sodium-rich plagioclase, and I'm going to talk about the different continuous and discontinuous processes here. So, on the left side, with the discontinuous branch of Bowen's reaction series, you'll see that you get olivine, produced at high temperature, and then whatever the chemistry that makes up olivine, when it's used up, you start actually making pyroxenes or augite, which is next. Now when we look at olivine and its relation to pyroxene, I'm going to throw up some chemistry on the screen, but don't worry about it. I don't ask you to actually memorize it. I just want to give you an idea of what's going on, because we know that this is changing. Or the chemistry is changing as you go through this series. So the first thing that you should know is olivine is, let's see, it has a magnesium in it, and I'm just going to put them in parentheses because you don't really know how it's integrated into the crystal. But it's a repeating structure with magnesium or iron, and then you have that separated with two silicon trioxides, or the silicates. And so that would be olivine. Oops. I'm going to write small so you can see it. Then, as you move down from here and you're using up all of this chemistry, or not using it up, but it's being used up and the conditions are changing, it's cooling and the pressure is changing somewhat, you end up with, which is XY. I know that looks weird, and then I'm going to put in parentheses because it's going to be silicon and aluminum, and then O6, and this is basically what pyroxene looks like. And pyroxene basically is these X and the Y's right here. These are variables, and they can include, it can be all sorts of different metals. The fact is as the iron and the magnesium is used up and the correct concentrations for olivine production, you start moving into the pyroxene production, which means it's a little bit different chemical composition, and it's not as stable as olivine. It's geology, but it's still chemistry is going on. Now, if you look at basically with the plagioclases, as you use up the calcium, right up here, it's a 2+. As you use up the calcium and you're going in this direction, the sodium Na down here starts getting taken into the plagioclase as the calcium gets used up. And then, of course, as you get near the surface of a continental crust, you're using up most of these things, and you start producing the potassium feldspars, the muscovite micas, and then, of course, the quartz, which is the last thing to fall out in this progression. And the last thing to note on here is I talk about the chemistry. Basically, the chemistry of the magma is determined by the series, and it can start anywhere in the series depending on what pressure and temperature is, and it doesn't have to complete the series either. Right? You can ending up with pyroxenes and not getting amphiboles or hornblends. But as you go in this direction, the color of the rocks, or I guess the shade of the rocks, again I'm saying color and I mean shade, is becoming lighter. So you have the mafic, which are the dark rocks, then you have the intermediate ones, which are right here, and then the felsic ones at the bottom. One other condition that we haven't really talked about, but I mentioned, is the presence of water in the magma. And what the presence of water does when it's in the magma is it changes the conditions under which this rock will melt. And that makes sense because when you think of ice and you drop salt, it's kind of a similar kind of idea, is the water molecules disrupt the rock just like the salt disrupts the ice, which is a water molecule, and it prevents it from bonding, which means the temperature at which water freezes drops because you can't form those crystals. Same thing goes on here. You have, if you add water, and that's what that little arrow means right here, is your temperature at which these will melt is going to drop. So the temperature is higher, right? It's higher in this direction. It's lower over here. And so what that means is this whole curve is moved in this direction, which means that with water present, the rocks melt at lower temperature. Pressures aren't changing all that much, but the temperature is. Now, what's interesting about that is we think there's actually more water in the rocks in the mantle than there are in all of the oceans and the fresh water on the planet's surface, which is pretty interesting. You look at kind of put this together in the rock cycle, which I ask you guys to do, is you look at the subduction points or divergent points for plates, and you're going to see that this is all mafic, right? This bedding plane right here, or not bedding plane, but this plate, as it slides under the continental plate, is an oceanic crust or oceanic plate. It's going to be basically a mafic or ultramafic, probably mafic rock. And then as it, just like as the boot gets lifted and you lose your shoe, the pressure on this is dropping because it's pulling down, which means that it's going to change the melting point of this rock. And there's water that's already present because it's getting pulled in by the ocean. So this is actually the mafic magma. But as the pressure and temperature changes, pressure and temperature is going to drop, right, as this magma chamber moves up towards the surface, and the different olivine and stuff is going to fall out first, right? So you get, I'm going to draw an arrow out here, you get olivine coming out first, and then right after that you might get the pyroxenes coming out. Now be aware this is all happening in the chamber. These chambers are huge. If you look at the picture on the website, I have Yellowstone magma chamber in there, and it's 600 miles or 400 miles deep. You know, and remember the continents are only 100 miles deep, so that's actually down in the upper mantle. It's a huge magma chamber. So these things are going on all over the place, and these minerals are raining out all over the place. Once they've solidified, you have to heat them up even more to melt them, so they'll rain out at the bottom of these things. But the idea is along subduction zones in these convergent boundaries, you get these partial melting of the subduction plates, which causes the felsic magmas, or the intermediate and felsic magmas to bubble up. When they first melt, they're not necessarily, it's mafic in many cases, or probably intermediate. Doesn't necessarily felsic yet. It has to go through a change as that chemistry changes as it comes up. And then we have these hot spots. Now the hot spots are interesting because they don't move. If you look at the plate movement for Hawaii is northwest, but it looks like the Hawaiian Islands are traveling, because the newer islands looks like they're traveling southeast, but in reality it's just because the plate's moving. And so in this direction, this would be, if you look at the Hawaiian Islands, go to Google Earth and you can look at it. It looks like the islands are moving, so the plate's moving northwest, but the islands look like they're moving southeast. I think I said northeast, but I meant southeast. Now with Yellowstone, which is basically what they're showing you here, the plate's moving in one direction. In this case, the plate would be moving southwest, I think is what North American plate looks like it's moving. And we have all of these basalt flows all over Idaho through Utah down into California as the North American plate moved over Yellowstone, or the Yellowstone Basin. And here's what the compositional changes in magma in the magma chamber, and these things are huge. So, and I'm going to show you another slide. Next slide will show you much more detail. But what happens is you have the magma chamber, and in these magma chambers you have certain pressures and temperatures, you know, and they all go together. I mean, it's not like they're separated. And so you might have a higher pressure and lower temperature here, might be a lower pressure, higher temperature here, based upon local conditions, right? Same kind of thing, higher higher, and obviously higher pressure as you move down. But there's some, you get eddies and flows, and you have mountains on top of these, which changes the pressure, etc. Anyway, as these olivine or pyroxene or intermediate rocks or intermediate minerals are forming, they fall out and they settle out on the bottom, right? And they make these little collections. Sometimes they may settle out and you might get these outgrowths that look like that, and you get solid rock forming inside these chambers. And if you look at it close up, this is what it is. Basically, you can assimilate the country rock, which would be the rock that's already, could be sedimentary rock, could be other igneous rock. And in these zones, near where you have these big igneous intrusions, you get, so in this area, you might get, anyway, you're going to get some metamorphic rocks. And as you move through the magma chamber, you might get a different kind of magma coming in one section, some coming up here, different kind here. You get the mixing. It's going to be different chemistry, different temperature, different pressures. It might be coming in at high pressure, right? Or it might be coming in at low pressure, depending on where it is, which changes the constituent minerals that are formed. But really, magma, it doesn't mix all that much unless it's very similar, or the viscosity is very similar. So keep that in mind. Then you look at the igneous rocks, rock textures, which is how we define rocks and how we define or name them, I guess, is what I should say. Is you get basalts and granites, or basalts and rhyolites or phenocrysts. All these things will determine what kind of rocks that you have. You have extrusive and intrusive rocks. So in this case, you have, it looks like extrusive rocks, where you're going to have possibly a basalt right here. I don't know. It's whatever's in the book. I don't know what they have in the book. I'm guessing. And over here, it looks like you have a granite, possibly. And when we talk about phenocrysts, when you look at here and you have phenocrysts inside, they are called porphyries or porphyritic rocks usually, which means that you have slow cooling for the big crystals, and then something changes and it cools rapidly for whatever reason, and you end up forming a lot smaller crystals. It's still a similar, or it could be different, it's a similar constituent, which means the chemistry is fairly the same. Then the last ones here, which are from the book, look like this is probably obsidian here, which it's basically a glassy texture. You can tell that it looks like a glass. And then you have vesicular, which means vesicles, a vesicular texture right here. This would be like, scoria, sorry, stuff you put around. This one's dark, sort of a dark color, but you get the red ones too, and they use it as landscaping rock. And then they have, it looks like a pyroclastic or some sort of figure here, where they've taken a very close look at fragments from probably a volcanic eruption that was violent, that caused these angular glass formation. So this would be like, an explosive lava coming out, could be a pyroclast or something like that, and that's what they're showing you there. And basically what this is supposed to show you, if you look at different, aphanitic would be A, B would be a phaneritic texture, which is, you can see the crystals with your eyes. Obviously they're different colors. And then there's the porphyritic texture, which is most of the C's here. And if we put it all together in the next slide, which kind of shows you how we identify rocks from all the minerals. So if you look in this slide, it goes up to 100%. You can even use a ruler when you look. You can take your ruler and you just block off 100 millimeters or 10 centimeters on a rock, and you can actually count the number of times based upon the number of millimeters that biotite appears or whatever, and then when you add them all up, because it's on 100, here you're going to have about 17% of that. If it's on the very left here, 70% is going to be biotite, about I don't know, 12%, 13%, no problem, 15% is going to be sodium-rich plagioclase, and then from about 32 to about 90% of your rock, so big chunk of that, which is about 60% total overall, is going to be potassium feldspar, which is the lighter colored feldspars, and then the clear quartzes is going to compose about 10% of that rock. And because you've counted out that it's a granite. That's pretty easy, right? I mean, you look at the intermediate rocks, you're going to be able to look at the different stuff like right here, about a little less than 50% of the rock or more. It could be even 50%. It's going to be plagioclase feldspar if it's a diorite. And then probably, again, you can lay a ruler over this. And how starting out as you look at the shade of the rock, just like we were talking about right here, you have darkness and specific gravity. We are going to do the specific gravity when you get your kits. The kits have come in, by the way, so you need to pick one up. But the specific gravity increases, silicate increases to the left, specific gravity increases to the right. So the greater amount of heavy metals makes the rock darker, which also makes it more dense, or gives it a higher specific gravity. And there you have it. You have a very easy way to identify the different types of igneous rock. I would like to add that if you get online, look at the PowerPoint, I have a bunch of really good notes related to this slide, so you can kind of read through it and it'll give you an idea of a deeper understanding of what it means to identify an igneous rock and what that means once you've identified it. And the last thing here is when we classify the rocks based on that last figure that you just saw, I'm just going to go through the different rocks, and it's going to be quick because I don't want to spend a lot of time because you guys have to get into your kits, and that's really where the fun is. It's not me talking about it. But the ultramafic rocks, now they're pretty rare, and the reason they're so rare is they either form very, very deep in the earth or they haven't been around, they haven't actually erupted in 2.5 billion years. So if you look at here we have the plutonic, which we think is most of what we find in the upper mantle, and we're actually drilling down there in the upper mantle to see what it actually, if that's actually the case. And then you look at the comatites, or actually the comatiites, sorry, they're the volcanic equivalent of plutonic. Now be aware that we haven't seen this in 2.5 billion years because the Earth has actually cooled down. Because when we talk about the heat at the center of the planet, the heat is derived from radioactive isotopes, and those radioactive isotopes are decaying and they're going away, or they're becoming less radioactive as they, decay. And here is a group of rocks that I want you to memorize because it's pretty these are the most common rocks. When we talk about the different kinds of rocks, we talk about the pairs. We have the rhyolite, which is basically lava from the continental crust, and a granite associated with that, and that's in the left. And then in the middle, which are these intermediate rocks, you have the andesites and the diorites. The andesite is the lava that you would expect to be associated with its other intermediate, these are the intermediate rocks, diorite. Now, and then if you go to the right, you have basalt, which is a very dark colored rock. You have it in your kit. Now you have gabbro as well, and you can see that they're very dark gray or black. The gabbro picture in this isn't so great because it has a lot of reflections on it, and that's actually much darker if you look at your specimens. But they usually, you're looking at compositions that we talked about a few slides ago. This is going to be the mafic, and this is going to be the felsic, and then this is the intermediate, which is between felsic and mafic. Pegmatites, which are basically granites with very large crystal inclusions. In this case, we have very large crystals that are embedded in other crystals, right? This is one crystal right here. Looks like a tooth. You have another, looks like mica, biotite or something, that's right here, very large sheet. And then of course you got your feldspars, which are these big, huge white inclusions. And then looks like you have inclusions of quartz or something like that. And then you have more biotite right here, some biotite right here, very large. This is a quarter, so this is bigger than a quarter. This is very large crystals, very coarse-grained, most likely felsic, and it's going to be an intrusive rock. Very rarely does this cool slowly if it's at the surface of the planet. And by definition, it's in the notes, pegmatites have to have crystals that are bigger than 1 centimeter. So when you measure them in their width, not their height. So you have to know where their crystal faces are, and you measure in there. They need to be 1 centimeter or larger. Then, of course, you have these other type of characteristics. So we have, whoops, my pen disappeared. So we have the obsidians, the scoria, pumice, which we've all, you've taken off calluses, and then you have the tuff, which is pyroclastic material such as ash that builds up and then gets compacted, and you get these big, huge igneous deposits. It's almost like sedimentary with the tuff, which is pretty interesting because it's raining out from the ash from the sky. And this is how you look at them when you're trying to classify them. You'll notice that their composition is felsic or mafic, just like the other rocks. Here you have pumice or scoria, and then obsidian, which forms across the felsic and mafic. It's just glass, basically. It's glassy. It's natural glass. And then the pyroclastic stuff is the tough, welded tough kind of stuff, and what we call volcanic breccia, which is just, think of volcanic bombs in a way. It's just a whole bunch of them. It's broken pieces. That's what breccia means, is volcanic broken pieces, I guess. But it's pyroclastic, which means it gets ejected. Now, and you look at the plutons underneath and the volcanic lava rock on the surface, and this basically brings everything together. And this is, in this case, you end up with stock, which is just an intrusion into the country rock, right there. The batholith, which is this whole big, huge thing right down here. You have the laccolith, which is an intrusion of a volcanic pipe that forces lava into a bedding plane, which means that they're separated right here. Excuse me. Which means this is going to be higher pressure as it gets pushed in, probably a lower temperature, right? So you can see how there are going to be different rocks formed here than there are formed down here. And then we have a dike, which is just an intrusion into the rock as it melts through the country rock. A sill, which is not a laccolith because it's basically as the volcanic, the magma moves up into the volcanic pipe or the neck of the volcano. It squeezes out, I don't know if that's a technical term, but it gets forced into the bedding plane, and you get a cross. It's a igneous cross bed when they call it a sill, just like a window sill. And then, of course, we have the lava at the surface that comes off, very small crystals. It's aphanitic crystals. The stuff that forms down here, that's phaneritic. And then, of course, stuff that may be forming down here in the sill, but then suddenly gets sucked up and pushed up like that. May be phaneritic to begin with, and then an aphanitic ground mass forms around that those phaneritic crystals, which means you get a porphyry. And then, of course, the ash, the lava flows, and then, of course, we have cinder cone, which is like scoria, things like that. And then, of course, this is Close Encounters of the Third Kind, right? If you guys ever seen Close Encounters of the Third Kind, which is, from a long time ago, but that's an old volcanic neck in Wyoming called Devil's Tower, which Karen actually posted on. And then there it is. There's Devil's Tower. It's an igneous neck of a volcano that is now eroded away. At least the volcano has eroded away. The neck is still there. So in summary, igneous rocks make up large parts of continents and oceanic crust. Silica is the primary constituent of magmas, even the mafic and the ultramafic. Temperature and the amount of silica in a magma determines the viscosity. As you look at stratovolcanoes or volcanoes that are continental, sort of like Mount St. Helens, continental volcanoes, They have a high viscosity and high they're explosive. How about that? Then you have divergent, convergent, transform boundaries. Hotspots are the origin of most magma. And geologists, including yourselves, identify igneous rocks using textures: aphanitic, phaneritic, porphyritic, and then the different subtextures there. Then you got extrusive and intrusive magmas determine the cooling rate. And that's pretty much it for chapter 4.